Okay, this is part 2 in our VSEPR shape tutorials, and I'm gonna put this in a chart where in the leftmost column we have the number of effective pairs, which is the lone pairs and the bonded atoms. We'll go over what overall geometry that makes the molecule, and the molecular shape is what's determined by the number of lone pairs. So this is determined by how the lone pairs push on the bonded atoms. I'll put BAs. And then in the rightmost column, we'll go over some examples. This one I'm going to make, there's an extra column here, and I'm going to call this the hybridization on the central atom. This one we're going to save for the next tutorial when we go over hybrid orbitals. Okay, so let's start with when you have two effective pairs, and the overall geometry is going to be linear when that happens. The molecular shape is also linear because all you can have really in this case is two bonded atoms. So two bonded atoms. You can't have a lone pair. So you can't have like an atom X bonded to Y and then like one lone pair there. So this is going to wind up being a linear shape. So here's an example. So if you have like something from column 2, like BEH2, these do not often make covalent bonds, but that's what it would look like. And you would get BEH like this. And the bonded angle here is going to be 180 degrees if it's linear between the two atoms. The next thing that can happen is if we have three effective pairs. So, alright, three effective pairs. And the overall geometry of this shape when you have three effective pairs is going to look like this. It's going to be like X, Y, Y, Y. And Y can be either a bonded atom or a lone pair. So the overall geometry is going to be trigonal planar. And there are two variations of the trigonal planar. You could have a regular trigonal planar, where this is where you have three bonded atoms and no lone pairs. An example of this is something we've seen before, like aluminum trihydride. So it's going to look like this, Al and hydrogen atoms here. And these are bonded, I think you could see 120 degrees apart. The next variation of a trigonal planar is when one of these is actually a lone pair and then the other two things hooked onto it are bonded atoms. So this is called, when that happens, this is called V-shape. And again, that's two bonded atoms with one lone pair. An example of this is like SO2. So SO2 would look like this. It's going to be a double bond with one oxygen, and then it's going to have like a lone pair here. And on my drawings, I'm going to put lone pairs in these containers just to emphasize the point that that is taking up space there, and it is still doing a trigonal planar. So it's still like a triangle where the angles are 120. Just as in the last video, I was explaining how the lone pair, when you have an electron domain that's a lone pair, it actually squishes this angle. So you should expect this to be a little bit less than 120. Okay, so I'll just put less than 120. As for another thing I kind of wanted to cover on this slide, I could kind of kill two birds with one stone. And this is actually if you have a 3A with the same atom attached, then this molecule, so this is 3A with the same atom attached, this molecule is going to be nonpolar. So if you have SO2, this V shape, it usually, unless the bonds are nonpolar, it usually results in a polar molecule. So you'll get a dipole here, and a dipole here, and a dipole here, and this will result in it being polar, since you'll get a net dipole pointing down like that on the molecule. Okay, so let's move on to when you have 4 bonded atoms. So I think you can probably guess that the variation, it gets a little bit more with each increase in effective pairs. So if you have 4 bonded atoms, the overall geometry is going to be a tetrahedral. And the first variation of that is if you have all 4 bonded atoms, that is a tetrahedral. So this is 4 bonded atoms with no lone pairs. An example, of course, is like CH4. These are actually the examples I used in the last video. The bonded atoms are 109.5 degrees apart. And this molecule is, if you have the same atom attached, if the same atom is attached, it's nonpolar. The next variation you could have is if you have 3 bonded atoms and 1 lone pair. This will result in a trigonal 3 bonded atoms with 1 lone pair. So we have NH3 as our example. Okay, and it has that lone pair, so I'm going to draw like a container there. And the angle here is a little less than 109 because of the lone pair, so it's 107.5. This shape, unless the atoms themselves are, the bonds themselves are nonpolar, this shape is usually polar, because they're all either going to point up, as in the case on this molecule, or all the dipoles point down. So they're all going to be going in a similar direction. The third variation you can have is bent. And that's when you have 2 bonded atoms with 2 lone pairs for a total of 4. So an example of that is when you have water. So you have H2O. Okay, and that's a bad electron domain. Okay. And this pushes on the angle, so this is 104.5. And this molecule usually is going to be polar, much like the trigonal pyramid shape. This molecule has a dipole either going up towards, since it's bent kind of like a V, it's either pointing up towards the O or away from the O. In either case, they're pointing in the same direction. So in this case, of course, they're pointing towards the O. Okay, so those are the 3 variations for 4 effective pairs. Let's move on to 5 effective pairs. Here's where we actually exceed the octet. So this is 5 effective pairs. I'll put a little star here just to note that this is where you break the octet rule. The overall geometry for 5 effective pairs is called trigonal bipyramidal. So there are 4 variations. The first variation is called a trigonal bipyramidal. And this, I think you could see the pattern I'm going in. Here's where you have 5 bonded atoms with no lone pairs. An example of that is PCl5. So on the phosphorus here, then it's going to have 5 chlorines that look something like this. The way that they get this shape is actually this forms like a trigonal planar, and then these points up here, these chlorines, actually form a pyramid with 4 sides, 1, 2, 3, and then the bottom side. Okay, and then it does it again right here. I can't draw very well, but this will go something like this. Well, yeah, I think that one connects to. Okay, anyway, so this is called a trigonal bipyramidal, and it's like you have a pyramid here and then another pyramid here connecting at the base, and one pointing up, one pointing down. So this one is going to be actually the bonding angles here between these 2 chlorines. You have 2 different types of bonding angles. Right here is 120. And the distance between these 2 bonded angles here and here is actually 90 between one of the top chlorines. But the chlorines that make up the pyramid, or the triangle right here, are 120. So this shape is actually the dipoles. I need to erase the shapes that I made here just so I could show the dipoles better. So the dipoles are going to go here, here, here. They actually all cancel out. So the trigonal, or the trigonal planar ones cancel out, and then you have this chlorine going up, this chlorine going down, so then those cancel out. So this molecule ends up being nonpolar if the same atom is attached. So if same atom is attached on all 5 locations. Okay, so moving on, our next shape is called a seesaw shape, or teeter-totter shape, and it's 4 bonded atoms with 1 lone pair. Here's an example that does the seesaw shape: sulfur tetrafluoride. So it's going to look like this. And then it's going to have 2 lone pairs, or I'm sorry, 1 lone pair right here. The reason they call it a seesaw, just to speed up this video a little, I'm not showing lone pairs, but of course you're going to have lone pairs on all these fluorines. But a little note on the shape. This is kind of like, there's a fulcrum, and then you have on a teeter-totter, it goes like this, right? And then you have like kid sitting here, and then they go up and down on the teeter-totter. So this is kind of like the fulcrum right here, and then this is the seesaw right there. So it kind of helps you remember the name of the shape a little. So that's where they get the name of that. Well, I think that's where they get the name, but to me, that's kind of what it seems like it might be. So this is 180, and the angle between these 2 is kind of like, so it's kind of like this piece right here, like this right here. This is kind of like that trigonal planar piece right here. So this angle is a little bit less than 120. So I'll put right less than 120. Because instead of this atom, you have a lone pair right there, so it's going to squish these 2 atoms a little bit closer. And this molecule ends up being polar. So because these 2 dipoles will cancel, you'll get a dipole here, and you'll get a dipole here. Those will cancel. However, you have this and this, and there's nothing for those to cancel with, so you'll get a net dipole going like that. So this molecule ends up being polar when you have the seesaw shape. Our next shape is called a T shape, and this is when you have 3 bonded atoms with 2 lone pairs, and it makes what's called a T shape. So if you have chlorine trifluoride, so you're gonna have, it'll look something like this, and it's analogous to this shape. So instead of these, there's 2 lone pairs there, so we'll draw right here and then another container right there. So it ends up making, I think you can see the T, so the T is like right here, like that, so that's the T shape. And the bonding angles on this are going to be about 90 right here, and from here to here is 180. This molecule ends up being polar. Okay, so because you'll have a dipole here, and dipole here, so these 2 cancel, and then that one ends up giving it a net dipole. So we have one more where you have, so I'm going to write continued, where you have 5 effective pairs. Again, the overall geometry is continued from the previous slide. And so here's the 4th variation. You could have something called, it's going to be linear. And this is when you have 2 bonded atoms with 3 lone pairs. And an example is, the halogens can do this weird polyatomic ion where it's 3 halogens stuck together. Chlorine and iodine usually can do this. Just because their radius is so big that you can get overlap and still have some stability in the molecule without it being too crowded. So this one's going to be a BR, and BR, and where that trigonal pyramid was is where all these lone pairs are. So I'm going to draw an electron domain here, here, and then there's another one right here. Okay. And then the bonding angle here, of course, is between these 2 atoms is 180 degrees. And keep in mind, it's good to remember that these are all based off of the trigonal bipyramidal shape. So this right here, again, is this piece right here is that trigonal planar part, and then these are the pieces that stick out from it. So if we go back again to compare, I put all the lone pairs on the one I just drew. I put the lone pairs right here, and then the 2 BRs were right here and here. I just decided to draw it left to right, though, instead of up and down. So it's important to remember that these are all based off the same geometry. They just differ in their number of lone pairs and bonded atoms. Okay, so this is the one where you have 6 effective pairs, and it's going to make a octahedral. So you could have 3 variations of this. You could have where they're all bonded atoms, so a octahedral, where all 6 are bonded atoms with no lone pairs. An example is sulfur hexafluoride, and it's going to look like this. Okay, and this shape actually ends up being non-polar, so all these dipoles, that one cancels with this one, it will cancel with this one, this cancels with this one, and this cancels with this one. So all the dipoles cancel, and this ends up being non-polar. Okay, if I go back to a slide, I forgot my linear molecule. This one should be non-polar because it's the same atom attached. You have to check to see, though, usually non-polar if it's the same atom. Alright, so let's go on to the octahedral. The bonding angles are going to be 90 degrees from here to here, and here to here. So this actually makes like a, this actually is going to make kind of like a square. And then you get like this four-sided pyramid up here. Like that. And then you get another four-sided pyramid right here on the bottom. Like that. So you get these four-sided pyramids that are connected at this square base right here. One pointing up, one pointing down. So you get 90 degrees on all the bonding angles. Okay, the next variation is going to be, is called square pyramid, and that's when you have 5 bonded atoms with 1 lone pair. An example of that is ClF5. That one will look like this. And you get a lone pair right here. So this one's going to make a square, kind of like the previous one, and then just one triangle like that. So that's why it's called square pyramid. The bonding angle is from here to here, 90 degrees, and this molecule ends up being polar, since there's nothing for this one's dipole to cancel with. That leaves us with one more shape. This is called a square planar. And this is when you have 4 bonded atoms and 2 lone pairs. An example of that is XeF4. So it's going to be Xe, and it's going to make a square, kind of like in one plane, and this guy will have 2 lone pairs attached to it. Okay, and then the bonding angles are 90 again, and the molecule ends up being nonpolar. Okay, so your textbook actually covers this pretty well. They have like really nice pictures, and then they show on page 348 the electron domain, and so these are like the overall geometry. So you could have a trigonal planar, and with the trigonal planar you could have a lone pair here, or all 3 bonded atoms. On the tetrahedral you could have all 4 bonded atoms, or you could have a lone pair here and 3 bonded atoms like NH3, or you could have 2 lone pairs and 2 bonded atoms like on water, and then those are all considered tetrahedrals. For the trigonal bipyramidal, again, you could have all 5 bonded atoms, or you could have a lone pair up here, or actually you could have like this one a lone pair, and that gives you the seesaw shape, because that gives you that fulcrum, and then there's the seesaw. Or you could have, let's see, or 2 bonded atoms on this one. Okay, or even 3 bonded atoms. So you could have all, or even 3 lone pairs. So you could have all 3 of these being lone pairs, and it result in a linear shape. But the overall geometry is going to be a trigonal bipyramidal. Then the book also breaks these down and shows you the molecular shapes also, so the different variations. So here's trigonal planar, and then these are the 2 variations. Tetrahedral, the 3 variations based on the lone pairs, and the trigonal bipyramidal, and it has the 4 variations, so seesaw, T-shaped, linear, and then the octahedral. So this one is a couple pages after the previous slide, and then they have some other examples. Some of them are the same, some are different than the ones I had. So I have a question at the very end here, and it's the your turn question. So on these 3 molecules, first draw the Lewis structure You don't need to get the shape right to begin with. I really highly suggest using pencil, because you're probably going to, once you have the overall Lewis structure correct, you're going to try to use this chart. Also, oh yeah, draw possible resonance structures it might have. Indicate the electron domain geometry. So use the chart and go by the number of bonded atoms and the number of lone pairs, and then that can tell you the molecular shape. The overall geometry is the number of electron domains it has. And then the fifth thing, indicate all the bonding angles. So for 3, 4, 5, and 6, basically you're using the chart that you just wrote down. Steps 1 and 2 are what we learned before. Okay, so here are the examples to try. So KRF2, CLO2 plus 1, and IF5. Okay, so let's see what you guys come up with on that.